Hi, this is Shoikat Majumdar. Our course code is BSPH101. It falls under the category Basic Science Courses. Course title is Physics 1. It is for the first semester students. Credit is 4. Prerequisite for this course is knowledge of 10 plus 2 physics. Course objective is basic concept of optics and its applications. We will discuss the interference of light. You have seen beautiful colors in soap films. How these colors are formed? These colors are formed due to the phenomenon of interference of light. As well as you can see this when some oil is fall on water or petrol is on petrol or diesel is on road, then you can see the patches of colors, beautiful colors in oils and on water films. The mechanism of these colors is due to the interference of light that is shown here in the presentation. Light is incidenting and it is reflecting back from different surfaces. They are maintaining the path difference. Under the condition of the path differences, they will produce constructive or destructive interference. Then the color in the fringes will form. Now, of interference of light. When two wave trains coming from coherent sources superimpose each other, produce alternate bright and dark bands. This phenomenon of light is known as interference of light. Now, what are the coherent sources? Actually, there is no existence of coherent sources. Coherent sources are the virtual sources. When two sources emitting light waves of same frequency, same or nearly same amplitude, and they must maintain a constant phase relationship, these sources are known as the coherent sources. Now, there are two independent coherences. One is temporal coherence, another one is spatial coherence. Now, here we are showing you the temporal coherence time and spatial coherence length. In temporal coherence time is a time the wavefronts remain equally spaced. It is evident from the picture. Wavefronts remain equally in space. That is, the field remains sinusoidal with the wavelength. In spatial coherence, the coherent length is the distance over which the beam wavefronts remains flat. This is how it is. Now we will discuss the next part, wavefront. A source of light spreads its disturbance in all directions in vacuum or in homogeneous medium. The points, those are situated at equal distance from the source of light, will vibrate in the same phase. Any moment, the continuous locus of each such point having same phase of vibration is called wavefront. Suppose you are dropping a stone in a pond, what will happen? The continuous crest and trough are produced and they will move towards the end of the pond. That means there is a wave there is a wave. Where we have dropped the stone, it is the primary source of disturbance. So from Huygens principle, each primary source of disturbance will produce the secondary sources of disturbance. So this is, you can see, this is the primary source of disturbance, this is the secondary source of disturbance. Now, the wavefront is the envelope of the wavelets. So secondary source of disturbance will also produce the wavelets. If you envelop in a semicircular way, then, or semispherical way, then this is a wavefront. Here in our case, AB and CD are the two wavefronts. If the point source is this, these are all the secondary wave sources, secondary disturbances. Now we are enveloping these spherical wavelets. So this is the primary wavefront, this is the secondary wavefront. First one is the primary wavefront to the center, and this is the secondary wavefront. Now wavefronts may be of different types: spherical wavefronts, cylindrical wavefronts, plane wavefronts. Suppose you are just switched on a torch. Torch is giving you the light, and a cardboard is placed inside the just along the path of the torch. Then the light will fall on the cardboard. The light, that is the plane wavefront. Suppose tube light is glowing, this is a cylindrical wavefront. So a small bulb is glowing, this is a spherical wavefront, it is going in all directions. Now coherence time. Coherence is a coherence time. Time interval for which phase difference remains constant is called coherence time. Phase difference is depending upon the path difference. We know phase difference is equal to 2 pi by lambda into path difference, where lambda is the wavelength of light used. If c be the velocity of light, coherent length LC is equal to c into tau c. Tau c is the coherent time. Now coherent sources can be obtained by two methods. One is division of wavefront, another one is division of amplitude. In case of division of wavefront, narrow sources are required. In case of division of amplitude, broader sources are required. For Young's double slit experiment, we can see the division of wavefront, and for Newton's ring experiment, we can see the division of amplitude. Young's experiment, already we know from our class 12 syllabus, continuous crests and tails are produced. When they are meeting in same phase, they will produce bright spots. When they are meeting in opposite phase, suppose crest tails, then it will produce dark spot. When crest, then bright spot. So this is how the interference patches are produced. Now, what are the conditions for sustained interference? Number one, sources must be coherent. Coherent means they have same frequency, that means same wavelength, amplitude is same or nearly same, and they must maintain a constant phase difference. Second one, the sources should be narrow. With the increase of slit width, the coherence property will be lost. And third one is the slit separation will be very small. Otherwise, overlapping of bright and dark points will hinder interference. And last one is separation between source and screen will be optimal. Now we will come to the point expression of intensity. Here in Young's double slit experiment, when the sources are separated by distance small d apart and the source and the screen are separated by distance capital D, consider two interfering sinusoidal waves. x1 is equal to a1 sine of omega t and x2 is equal to a2 sine of omega t plus delta are superimposing each other, and these two waves having a phase difference of delta. After superposition, the resultant wave becomes x is equal to x1 plus x2, and after doing this we will get this expression. Now consider a1 plus a2 cos delta is equal to r cos theta. and A2 sin delta is equal to R sin theta. Substituting these two, we can get the expression of displacement x is equal to R sin omega t plus theta, where R represents the amplitude and R is equal to a square a1 square plus a2 square plus 2a1 a2 cos delta. We know the intensity is the square of the proportional to the square of the amplitude. So I is equal to, we can write a1 square plus a2 square plus 2a1 a2 cos delta. If a1 is equal to a2 is equal to a, then r square becomes 4a square cos square delta by 2 after mathematical calculations. Thus the intensity is I is equal to 4a square cos square delta by 2, where a is the amplitude of the waves and delta is the phase difference. Now come to the condition of constructive interference and destructive interference. Constructive interference means bright fringes and destructive interference means dark fringes. Now cos delta, its maximum value is 1. So it is the value we will get 1 for cos 2n pi. Thus delta is equal to 2n pi, where n is equal to 0, 1, 2, 3, etc. And its corresponding path difference is n lambda. So constructive fringes or bright fringes will produce, constructive interference will occur or bright fringes will produce when delta is equal to 2n pi, where n is the 0 integer numbers, 0, 1, 2, 3 natural numbers, and path difference is n lambda. For destructive interference, the minimum value of cos delta is -1, so this becomes cos is equal to 2n plus 1 pi, thus delta is equal to 2n plus 1 pi, n is equal to 0, 1, 2, 3, etc. And its corresponding path difference is 2n plus 1 lambda by 2. As you know, path difference is equal to 2 pi by lambda, phase difference is equal to 2 pi by lambda into path difference. The ratio of the maximum to minimum intensity is Imax to Imin. Imax is equal to cos delta is, if it is 1, then this value becomes a1 plus a2 whole square, and Imin is equal to cos delta -1 means a1 minus a2 whole square. If we plot the intensity distribution pattern, it will be like this. This is the, at delta is equal to 0, we will get this one is equal to maximum, and delta is equal to, again when it is pi by 2, cos pi by 2 means 0, again cos pi means 1, cos 3 pi by 2 means 0. So this is how dark fringes and bright fringes will produce. So our next question is, if it is bright fringe, it is a dark fringe, then whether the energy is conserved or not during the interference phenomenon. So come to this point, energy conservation. So Imax is equal to, the formula is a1 plus a2 whole square, and Imin is equal to a1 minus a2 whole square. So I average is equal to Imax plus Imin by 2. So this is equal to a1 square plus a2 square. So when there is no interference, I is equal to I1 plus I2 is equal to a1 square plus a2 square. Thus the energy is conserved. Actually in interference phenomenon, energy never be created nor destroyed. Energy is only redistributed from bright fringe to dark fringe or dark fringe to bright fringe. That means energy redistribution will occur. There is no destruction of energy or no creation of energy. There is only redistribution from bright to dark or dark to bright. Next part is fringe width. What is fringe width? Separation between two consecutive bright and dark fringes is known as the fringe width. Separation between two consecutive bright or dark fringes is known as fringe. If we come to this, to the previous slide, we can see these are the bright fringes, this is the dark fringes. So separation between these two, so bright to dark, bright to bright, consecutive to bright means this is the fringe width. This is the fringe. This part is the fringe width. Again, this one is the fringe width. This one is the, even similarly, this is the fringe width of the bright fringe. Distance between two consecutive bright or dark fringes is known as the fringe width. Now, how we can find out the thickness of a thin transparent sheet, generally mica sheet? Consider when the light is coming from S1 and S2 and it is coming to point O, then there will be no path difference. It will produce a bright fringe. or constructive interference will occur. Now, along the direction from the light from S1 to O, a mica sheet of refractive index mu and thickness T is placed. What happened? Now, the bright film that is produced at point O, it is now shifted to the point P. Shifted to the point P at a distance of widest from the central fringe. Now we can calculate from the concept of velocity of light, we can find out the thickness of this one. Now, after the calculations, the thickness becomes T is equal to n lambda mu minus 1. This n lambda comes from condition for the bright fringe and mu minus 1. Alternatively, we can write T is equal to y dash lambda beta mu minus 1, or beta is equal to lambda capital D by small d is a fringe width. So this is how, if we know the value of the refractive index of the mica sheet or any transparent sheet, and the wavelength of light used, we can measure y dash from the telescope, and beta that can be easily calculated as we know the wavelength of the light used. D and capital D and small d can be measured. So you can find out the value of T. T is the thickness of the mica sheet. Now, interference of thin films, that from the very beginning we have discussed during the we have mentioned actually, not discussed, mentioned actually during the soap films or water film on oil or oil film on water. We have discussed this thing. So thickness, this is the, suppose this, there are two planes separated by thickness T. When light is coming from A to B, one part of light is reflected, another part is transmitted. Again this light is reflected from C, then refracted. Again this part from D is reflected, then reflected. From E some light is transmitted, from C some light is transmitted. So when the light coming from this path A, B, R1 and A, B, C, D, R2, there is a path difference. There is a path difference. These two lights R1 and R2 are from reflected light. This path difference is Bn. There is a path difference Bn. So when there is a path difference, there is a condition, either it will produce bright fringe or dark fringe. There is a phase difference definitely. Depending upon the path difference, phase difference will produce. Either it will produce bright fringe or dark fringe. Another one, for this transmitted lights T1 and T2, there is also a path difference. This one is Ck. So for this transmitted light, there is also bright fringe and dark fringe. So interference can produce by the two methods. One is by reflection, another one is by transmission. So we can calculate the path difference between the two reflected rays R1 and R2 is 2 mu T cos R. This is the angle R, plus minus lambda by 2. This plus minus lambda by 2 appears due to change in medium. This one is air, this one is a medium. That's it. There is a one term plus minus lambda by 2 is appeared. So for constructive interference, this path difference is equal to n lambda. So you can write 2 mu T cos R is equal to 2n plus minus 1 lambda by 2. For destructive interference, the condition will be 2n plus minus 1 lambda by 2. So lambda by 2 will cancel out. This one becomes 2 mu T cos R is equal to. But for the method of transmission, these two lights T1 and T2 are coming from the same mediums. So there is no introduction of this extra path difference lambda by 2. Again we can calculate this path difference Ck is equal to 2 mu T cos R. For constructive interference, 2 mu T cos R is equal to n lambda. And for destructive interference, 2 mu T cos R is equal to 2n plus minus 1 lambda by 2. We have taken n is equal to 1 to 3 as there is a minus term. For plus, it will start from 0. For minus term, it will start from, n will start from 1 to 3. And it is all integer numbers. Now, wedge shaped film. If these two boundaries glass to air boundaries, another is air to glass boundary. There is air. It has some refractive index. When light is falling onto this one, so this light will reflected back from this glass, and after the transmission it will reflect it from the bottom edge, and then some light will be transmitted to this. So C and E are the reflected lights, and there is a path difference. So for bright fringe, if we consider this one, interference pattern will be observed here for transmitted rays, and the conditions are for bright fringes 2 mu t is equal to 2 mu t cos r is equal to n lambda, and 2 mu t dark fringe 2 mu t cos r is equal to 2n plus 1 lambda by 2. I have taken n is equal to 0, 1, 2, 3. Now we will come to the division of wave front, and its famous experiment is Newton's ring experiment. This is a Newton's ring fringes. This is the fringes like rings. That's why it is named as the Newton's ring. Newton performed the experiment and got the rings. Suppose this is a source of light, monochromatic light. We are using in the laboratory in sodium vapor light. It is made to pass through some convex lens, and this light made parallel and made to fall on the transparent glass plate. Some part of light will reflected, and some part of will, after the reflection, it will come back to the microscope, and depending upon the path difference we will get the interference fringes, and these fringes will be circular. As why circular? As the plano-convex lens, it is placed on some glass plate. The point of contact between the plano-convex lens and glass plate is just a point. So fringes are produced centering the point of contact between the plano-convex lens and glass plate. So around the entire plane surface of the plano-convex lens, light is falling, and interference fringes are produced, and this is why this rings, the fringes are circular. Now, for Newton's ring, we will consider dark ring. For nth dark ring, we can calculate the radius of the nth dark ring. We are writing it as Rn square. Radius square is equal to n lambda r by mu. Mu is the refractive index of the material of the medium that is enclosed. This is the, here it is mu is equal to, mu is the air, that's why here mu is equal to 1. This is the place where the medium is enclosed. If it is oil, then it will be the refractive index mu oil. If it is water, this will be mu water. But in our case, this is mu is equal to air. It may be oil, water, everything, anything. So come to this point, Rn square is equal to n lambda r by mu. N is the order of the ring, and mu is the refractive index of the enclosed medium. So diameter of the nth ring becomes dn square is equal to 4n lambda r by mu. So if we take the diameter of n plus m plus nth ring, this is becomes dn plus mth ring 4n plus m lambda r by mu, and for dn square it is already given. So from this two, subtracting dmn square minus dn square, we can calculate the wavelength of light, unknown light. So lambda is equal to mu dm plus n square minus dn square by 4mr. This lambda is the wavelength of the unknown light, mu is the refractive index of the enclosed medium, m is the difference between rings m plus n and n, r is the radius of curvature of the plano-convex lens. What is radius of curvature? Radius of curvature, what do you mean by radius of curvature? Any plano-convex lens is a part of a sphere. So radius of the sphere is the radius of curvature of the plano-convex lens. So r is the radius of curvature. It is mentioned here. Now mu air is equal to 1. So wavelength of the light for air, we can measure dm plus n square minus dn square by 4mr. Thank you.